Hi there. So the paper we're looking at today can take the code on the left, which is written in Python, and can output the code on the right, which is written in C++. Now the point here is that the code on the right does the same thing as the code on the left, so it is implementing the same function. The surprising thing here is that this model that takes the Python as an input has never been explicitly trained to output C++. So this is an unsupervised translation model. And that's the cool thing about this paper is that by having no supervised signal at translating source code languages into one another, it can perform pretty well at the task nonetheless. So we're going to look at this paper. It's called Unsupervised Translation of Programming Languages by Marie-Anne Lachaud, Baptiste Rosière, Loïc Chanusso, and Guillaume Lompel at Facebook AI Research. As always, if you like content like this, consider sharing it out and leaving a like, and also leaving a comment if you have something to say about it. They say a transcompiler, also known as a source-to-source translator, is a system that converts source code from a high-level programming language, such as C++ or Python, to another. They say transcompilers are primarily used for interoperability and to port code bases written in an obsolete or deprecated language, such as COBOL or Python 2, to a modern one. So for Python 2, you might know this tool that's called 2-to-3. So 2-to-3 is a tool that ships with the Python 3 standard library, I believe, that allows you to take Python 2 code and produce Python 3 code. And that is to kind of push people to convert their old code bases of Python 2 to the modern Python 3. Now 2-to-3 is handwritten program. It has specific rules built in that the programmers know if we modify Python 2 like this, Python 3 gets out. For example, the print statement in Python 2 requires no brackets, so we make a rule that whenever there's a print statement with no brackets, we'll add the brackets such that it's Python 3 compliant. Most of this code will transform the source code first into an abstract syntax tree, modify that, apply specific rules to that, and then output the language from the abstract syntax tree. Now the problem here is manifold. First of all, there can only be so much translation as there are rules. So every one of these rules has to be coded as a modification to the abstract syntax tree, and every one of these rules is handcrafted and therefore needs sort of human ingenuity. Humans need to go and write these rules of how to transform one language into another. And oftentimes, this doesn't, even though you can write these rules, oftentimes whatever comes out is sort of a bit of a cryptic source code, because you kind of have to make sure that your rules cover all the possible things, and the source code that comes out is oftentimes very cryptic and a bit hard to understand because it's been sort of expanded and formalized to make sure that it still does the same thing as the original source code. Now, for Python 2 to Python 3, this is still easy, right? These languages are extremely similar because it's not that big of a step to Python 3, except if you use very low-level language constructs or language features which have been obsoleted with Python 3. On the other hand, if there's something like COBOL, so a lot of this old banking code or insurance code or government agency code, whatnot, is written in these really old programming languages, and they've been kept alive by these old school programmers that are slowly but surely all retiring now, and there are just not many new programmers around that can support these languages, and the languages themselves aren't really updated that much anymore. So you would like to transform COBOL into something like I don't want to call Java a modern programming language, but it is used in modern times. I'd rather not call it modern per se. Java itself is a beast that's been sort of supported since forever. But in any case, you would like to transform something like COBOL to something like Java, where you have a lot of programmers that can develop and further develop your code. This is much harder. COBOL and Java are much more away from each other than are Python 2 and Python 3. So what you would like to do is you would like to have a tool that is like 2 to 3, but humans, because now if you want a tool like this, you need someone that's really proficient in COBOL and Java in order to write a tool like this. And you need lots of them, and they need to invest lots of time. What you would rather like to do is you would like to learn a system that translates from one language into another such that the meaning is conserved. And this, of course, is exactly the domain of natural language machine translation, except it's source code. So we all know that we've all realized in the last years that things like Google Translate have become extremely good at translating. So they say right here, although neural models significantly outperform their rule-based counterparts in the context of natural language translation, which is Google Translate is all learned right now, they say their applications to transcompilation have been limited due to the scarcity of parallel data in this domain. So what's the problem with just going and saying, oh, we can build really good neural machine translation models. Let's just apply them to source code. The problem is if you build a neural machine translation model, say something that transforms English to German. So you have the word hello and you output hello. Now you can do it not with just one word, but with entire sentences and so on. These models, they usually, or in the classical sense, what they need are parallel corpora, which means that you have documents that are written in many languages, and you can guarantee that they mean the same thing. So this is a supervised signal. One example of this is, let's say, press releases of the United Nations. So the United Nations will make some press release and they will then have professional translators translate that press release into all of the different, or into many different languages. And so you can pretty much guarantee that these mean the same thing. So these pairs of documents or triplets or whatnot, they are supervised training data for a machine translation model that translates from one language into the other. And the neural machine translation models rely heavily on these parallel corpora. For source code, you just don't have that as much. You don't have big code bases in great numbers where the exact same thing is implemented in one language and in the other language. There's just not that much data available. It is the case that sometimes let's say in the case of Torch, it started as Lua and then it went to PyTorch. And the developers had to translate the code from Torch to Python. But in the same step, they've also made improvements. They sort of re-engineered and reinvented the framework and made it better. And so you can't really say these are the same things. And likewise, there's not a lot of code available where the same thing is implemented in two languages. So we just don't have these parallel corpora for the source code translation. So rather what this paper does is this paper goes into unsupervised machine translation. Now, what does unsupervised machine translation mean? Unsupervised machine translation, you imagine I have just a big database of documents, and these documents, I know they're all in English, okay? And I have this other big database, and I know that they are all in German. I just know their documents are in German, but they don't correspond to each other. They're just German documents, and over here they're just English documents. I don't say that these two here are somehow the same. No, I just have a bunch of German, a bunch of English. They don't even have to correspond. They're just text. And now what I want to do is I want to learn a shared embedding space. I sort of want to learn a shared space of embeddings for these two languages such that similar things are mapped to the similar place. So if these two documents just happen to talk about the same thing, I want them to be mapped to similar spaces in this shared embedding space. So I'm going to have one model, a single model, where I input the text and it goes into this shared embedding space, okay? Now, this is unusual because usually in machine translation, if you translate from English to German, then you'll have your dedicated model that takes as English as an input and German as an output. And that would be a different model than one that takes even German as an input and English as an output, or French as an input and German as an output. In this case, we have this process right here and this process right here is the same model. And then the decoder that translates this, of course, now we have the encoder embedding, and then the decoder that actually translates to a language is also going to be the same model. So it's the same model that translates to English, then it translates to German. So first of all, how do we make the same model? Let's say we have the perfect encoder, right? This is E, the encoder, the same encoder for all languages. Let's say we have the perfect encoder and it can map whenever a sentence means the same thing in different languages, we can completely map it to the same point in embedding space, irrespective of the language it comes from. Now, how do we tell the decoder, which is also the same model, like how does it know what to do? This is a little trick where you take this embedding, so you take the input, you put it into your model, I don't even know how you go this, and then your output is going to be autoregressive, right? So you decode one token at a time. So you decode this token and then you feed it back into the model, and then you decode this token, you feed that back into the model, and so on. This is an autoregressive language model. And the trick here is that the very first token is a special token that describes the language you want to output. So here you say, I want German. And then you let the model decode its thing. And by conditioning on this token right here, it knows it should now produce German. You will simply, during training, you will simply put the token here. And if it produces something other than German, that's a loss, right? So it will learn to produce German after you produce this tag. All right. So what we need is an encoder and a decoder such that in the encoder we can put in any language text and it will map to the same space the things that mean the same things, and we need a decoder that can produce any language given this first thing. Now the decoder should be fairly easy, right? If we have a shared vocabulary between the languages and we always put this token, the decoder is not a problem. You can just learn the decoder in a straightforward way. But the encoder is going to be a problem. So how does the encoder map the different languages to the same space such that the same things are ending up in the same place? It seems a bit counterintuitive, right? Because it doesn't know which things correspond to which things. Now, the first thing you need is a shared vocabulary here. Since we are in a shared space right here, what you need is a shared vocabulary. So you tokenize all of the text with a shared vocabulary. And this vocabulary is going to consist of sort of word pieces. Now, if you don't know what word pieces are, in a word piece tokenization, what you would do is you would split words into so-called word pieces. So, for example, hello right here might be split into two word pieces. The first word piece might be hey, and the second word piece might be LLO. Okay, there is usually like some kind of indicator here that this is the end of a word and so on, but we'll simplify. And hello right here would be HA for the first token and then LLO for the second token. And these kind of word piece encodings, since the smallest units are going to be the characters themselves, they ensure that you always have everything is in vocabulary. You have no out of vocabulary tokens. But here you can already see that if we tokenize the languages like this, and then we use the same encoder, so the same encoder will pop them into this shared space, that means that to the model, this and this looks like the same thing. It is the same thing, right? It's the same input token in different languages. Now, as you can see, this comes from the same word. The low at the end in English and the low at the end in German, it comes from the same word. So, it's fair to assume that since it's the same input, it's going to be mapped into a same embedding space right here. Or since these things are usually context dependent, we can say in a similar embedding space or a close embedding space. But certainly the initial vectors are the same. That is already half the task, right? So by tokenizing in this way, we have already mapped part of our languages, even though they're just different languages, we have mapped the same word to the same space. And this relies on the fact that in this case, for example, English and German, and for example, French, they have significant overlap in their words as such. So the word hello and the word hollow, they are almost the same word as letters, as word pieces. And these shared embedding techniques abuse sort of the fact that these languages are close. They'll say, there will be some word pieces that are going to be the same in these languages. And naturally, because they're the same, they'll end up in the same place in embedding space. And because that now you have so what these embedding techniques do is they simply figure out the statistical relations between the word pieces. So if two things appear together often in the same context, they'll be mapped into the same space as well. So it would realize there is a lot of times where ha and he appear in front of this low thing. So I should probably map the ha and the he to the same location in embedding space. So the same relation to the low. So they would end up at the same place. So now you see, even though these word pieces are different, like they get different IDs, they'll be mapped to the same place in embedding space because their relation to the low is the same, and the low themselves are being mapped to the same place because they are actually the same. So you can see that this partial overlap between word pieces in the different languages combined with the shared embedding pre-training results in these token across the languages, results in an alignment of the embeddings. So naturally, the things that mean the same things are going to be in the same places in embedding space, either because they are the same or because their statistical relation to the things that are the same is the same. It is sort of like these ha and the he are like synonyms in this shared language. So if you jumble all the English and German text together, the model thinks ha and he are synonyms and therefore maps it to the same space. This happens exactly the same if you only have one language to true synonyms. So this would exactly be the same thing in this case. All right, so now we have different languages. We have a single encoder where we can input any of those languages, mapping it to the shared space. The decoder can be trained by simply giving it this indicator token right here to decode the appropriate language. So now the question is, how exactly do we train this such that this happens? Now, there's one caveat. In programming languages, of course, we still have to check whether that's the same or not. And we know that in programming languages, a lot of programming languages, for example, the word if is the same, right? So if you tokenize Java or Python or C++, the word if is the same. And likewise, there is a lot of overlap between the different programming languages. And that exactly is this correspondence to here. These models use the parts that are overlapping, either tokens themselves, or this can also be grammatical constructs and so on. They can also be overlapping and therefore mapped to the same space. So if a construct is used in the same way, this can be in higher layers, this can induce the same effect. And they'll use that to map the result will be that the similar things in these languages will be mapped to the similar spaces in embedding space. Now this makes this example a bit weaker because that means this method would work exceptionally well for something like Python 2 to Python 3 because they of course have like a lot of overlap of syntax and keywords and constructs, whereas something like COBOL to Java, it's more, let's say, doubtable that they will work so well. In this paper here, they've chosen C++, Python, and Java, which do have significant overlap, but especially something like Python to Java, of course, there is a lot of a difference, or Python to C++ as well. Python is not typed, and so you can see a bit of the difficulty is already in the paper here, but you have to be aware that this works less and less the less this shared overlap is given. All right, so how do you train these models? And remember, we don't have parallel corpora. We are simply reliant on having databases from having big repositories of Python code, C++ code, and Java code. And they don't correspond to each other. So the first thing you do, and as I understand it, you can do these things in parallel, but there are 3 different objectives that achieve 3 different things in these models. The first objective is the cross-lingual masked language pre-training. Now the models here are going to be transformer models with encoders and decoders, and that's comes from the Attention is All You Need papers and various other papers like this. I've done videos on those if you want to see that. This masked language model pre-training, however, is from the BERT paper. So BERT, if you don't know what that is, I've also done a video on that. This simply trains the encoder. So this is to train the encoder. What you would do is you would input code. So usually in masked language model, if you train the encoder, you input code with tokens like hello there. You would then, so this is your input, you would then mask some of the tokens. For example, here the low and the maybe the entire word there, you would scrap that. You would put it through your encoder, which is this transformer model like BERT, and then BERT is supposed to reconstruct hello there. Okay, BERT is supposed to reconstruct these 2 tokens, like it doesn't see them, and you ask it, what did I cross out? And it needs to reconstruct that. So you train the model to reconstruct these masked tokens. And the research on BERT and other things has shown that if you train with this objective, the encoder sort of learns about the structure of code. It learns which tokens and which constructs often appear together, and therefore it learns something about the structure of the input. And that means it can create whatever is up here is a good and meaningful embedding for these things that tells you something about the statistical coexistence of tokens. And of course, since we're doing this with all the languages, so the Python goes in here, C++ goes in here, without telling the model what it is, you just throw it in there, right? Java goes in there. By tokenizing it, and you see an example right here, so if this right here is C++, but in Python this would also be if, and since it needs to learn a single encoder for all of these languages, and since the tokens overlap partially, it is going to result in exactly what we want, namely a shared embedding space where even though the input comes from different languages, it is mapped, similar things are mapped to similar places in the embedding space. All right, so the masked language model pre-training very quickly is you take a piece of code, like here on the left, you mask out some of the tokens, here you can see them in this mask, and you simply ask the model, the encoder, to reconstruct those things, okay? So this is just for the encoder, as far as I understand it. The encoder doesn't see the thing back here. It simply sees this, and you tell it, please reconstruct, please tell me which words or which tokens I clipped out here. And it's supposed to tell you, okay, the first one is if, the second one is int, and the third one is the I. Now, if you consider what the encoder has to do here, so if you were to see this, then that pretty clearly, you could guess that that is an if. Of course, it's not 100%, but this is just pre-training, right? So you train it to output if here. Now here, you have to do a little bit more inference. Maybe you've seen this for construct a bunch of times, and you can see that this is compared here and this is added. So probably it's an integer, right? And then in the last thing, this is even more complicated. If you don't see that the I is here, you somehow have to guess that what it is. It's not clear, right? But you can guess that, okay, there's a local variable I right here, and probably it's going to be used somewhere in this block. Now, this here isn't I, and I don't see I anywhere else, so probably I goes in here, which makes sense because it's an integer and prime is an array, and integers index arrays and so on. Okay, so this is what the model does first. The second thing is we need to train the decoder somehow. How do we train the decoder? In a very similar way. We make the decoder do denoising autoencoding. Now before, we just had single tokens. We just asked the encoder to reconstruct tokens. So the encoder is this box right here. This colors. This box is the encoder, and the actual part that's going to predict these words is going to be one classification layer on top that is going to predict for each position the individual word. Now this is just for pre-training. After the pre-training, you scrap that and you attach it to a decoder. So you attach whatever you got out of the encoder to a decoder. And the decoder will output in an autoregressive way one token after another, right? It would output a token right here, and it feed that token back into the decoder, saying, okay, here's what I've produced. Now produce the next thing. It would produce the next token, and so on. So it would produce token after token the output. And now, as I said, I'm not exactly sure. I think they're doing all of these things at the same time. So this would still be here, but the information would just be routed in two different ways, or maybe they do it one after another. It doesn't really matter, but what matters is in this thing here, you now train the decoder. I mean, you train it jointly with the encoder, but you also involve the decoder. And you do this by doing something very similar. You corrupt a piece of code, and you get corrupted code. Now you can see part of this corruption is masking, like you did before, but also part of the corruption is like here, you scramble some of the tokens, right? It was this over here. You just jumble some of them around a bit. And then you also drop a token. As you can see, the one is dropped. And you simply, so you don't show this to the encoder or the decoder, you input this corrupted code into the encoder, and then you ask the decoder to give you back the original code without showing it the original code. So the task for the encoder decoder for the entire model here is, if you see this, here is corrupted code. I have corrupted it in various ways. Please tell me what I originally had. Now the masking, it does the same as before. It sort of infers it. This thing here, it says, well, probably this isn't really correct. You don't even tell it where the errors are, right? Before with the masking, you at least told it where the errors are. Now you don't even tell it where the errors are. So it needs to recognize this here is probably correct. This isn't. This, I'm going to rewrite this to that. Okay, and it does this one token at a time. So it first goes int, and it needs to output the correct thing. I hope the difference is clear to the masked language modeling, which involved the decoder. And here also is the first time where in the encoder you prepend this Java token. Now this, as you can see, it still goes from the same language to the same language, but this is where you train the decoder to output a given language. So here with the token. Again, this is the same decoder for all the three languages. The only difference here is every time you simply provide it with the special token at the beginning to tell it which language it should decode right now. So this now we have an encoder that maps all the languages to a shared space, and we have a decoder that, conditioned on a token like this, can output valid code in that thing assuming this here was corrupted code. Now, since the encoder is shared, it should map the same kind of corrupted code of the different languages to the same place in the embedding space. And therefore, this would already be enough to have this model that we desire. We can input some code. It doesn't actually have to be corrupted, right? We can just input some code in one language and ask the decoder to output the other language. And this works, but it doesn't work super well. And here the authors go for another idea from the unsupervised machine translation literature, which is back translation. So back translation is a technique where you can tune an unsupervised machine translation model in a way that you would tune a supervised one, but of course you don't have supervised data. So what's the plan? You will produce the data yourself using your own model. So the plan is pretty simple, and it's actually contained in the back translation name. So if you have a piece of code, what you would do is you would first use your model to translate this to another language, any of your choice. Now you have no clue whether this thing here is correct or not. You have no clue, and you have no way of assessing it because you don't have ground truth. What you can do is use your model again, or actually use a second model that you train in parallel. I believe in this case they could use the same model, but that could be unstable and so on. But in any case, you can use your system again to translate it back to your original language. Your system can do that, right? And here, whatever you get as an output, you know the ground truth. It's whatever you started with. So now you can compare what comes out to what you started with. The difficulty, of course, is if there's a mistake, you don't know which of the two models made a mistake. And so it could be that your original translation model made a mistake, or it could be that your back translation model made a mistake. And you have to find a loss function that kind of punishes both equally, or you simply keep one sort of constant and loss-free and train the other one, because there's going to be a sample where you have C++ as an input, and then the intermediate language is Python. So all of the models sort of get trained once as a source to target translator and once as a target to source translator. But I hope the objective is clear from the back translation. So now with the back translation, you train the models to go from one language to another language. Okay, and that's the final goal. Even though you do it without supervised data, you now have a model that can encode things into a shared space, that can decode into a language, and that is attuned to translating from one language to another language. So that's it. This is all. How does this work? Now for evaluation, the question is, of course, how do you evaluate models like this? For evaluation, they go to this website called Geeks for Geeks, and this is an online platform, sorry about that, with computer science and programming articles. It gathers many coding problems and presents solutions in several programming languages. Okay, so this is a website that teaches you to code, and it will have like an exercise, please do this. And then it will provide solutions in the different languages. Now, why is that cool? And they have an example. They have an example right here. Why is that cool? Because not only can you be relatively sure that these different functions that you have here do the same thing, but you can also be relatively sure that they are implemented in the similar way. Right? Because what this website is trying to do is it's trying to teach the people how to code up an algorithm that they think up in their head. And therefore, not only is the solution correct and the same, it is implemented in the same way. As you can see here, the construct, there's this if construct is everywhere, the else if is everywhere. So even though some of the languages might have specialty things for implementing some algorithms, these are really the same the same expression of algorithmic thought in the different languages. So that is a perfect parallel data set. The problem, of course, is that there's not that many. So it is good enough as a test set. It is not good enough as a training set. But given that it's a test set, you can just have these as test set, and then you can input the C++ and see whether or not the Java comes out. The problem here, of course, is that even though this is very clear, there are still, sort of many variations of how you can implement that to even express the same algorithmic thought. So metrics from natural language processing like BLEU just aren't going to be very good because they look at n-gram overlap, and you can write this function with very different n-grams and still be very, very valid and correct. And also, exact match is not going to be really the gold standard here. So what they do is they create a set of unit tests where for each of these functions they check their input types, they randomly generate a set of inputs, look whatever comes out, and if the same thing comes out in all of their test functions, they consider this a good unit test for that function. So whenever your model now produces, let's say you input Python, it produces a C++, you simply put these unit tests through the C++ function you produce, and if they produce the same output as the original Python function when on the same inputs, then you consider the unit test to succeed, and you consider the function to be correct. Now this, of course, this isn't it is super duper gold standard, especially with random inputs, because usually what you want to do is test sort of corner cases, but it's better than anything else so far. Now, I've been a long disadvocate of unit tests, honestly, because I think whenever a human writes a unit test, then they're probably, since they have already implemented the function itself, they're probably going to make the same mistakes, or they're probably just going to replicate the code and thinking of the function in the unit test itself, and therefore it doesn't really get you anything. I guess in large organizations you write unit tests so that someone else doesn't screw up your code, but in this case it would actually be cool, because now as a human you could simply write a bunch of unit tests and then let your transcompiler do the heavy lifting, and you simply check whether or not the output is good. All right, so how does this do? Here you can see they have some baselines. The C++ to Java, as I understand it, is a commercial system, and the Java to Python is an open source system. Both are human experts that make up these rule-based systems on how to translate code into other languages. Now, if you do what they have here is transcoder beam 1, which means a beam size of 1. So if you don't know what beam search is, very shortly, beam search is like if you decode from your language model, you can either always take the next token that has the highest probability, this would be greedy decoding, or a beam size of 1, or you can sort of always keep the top n hypotheses of what the most likely output is, as you can keep that as you can keep the top 5 in memory and always decode these 5 on, sort of like you have a mini batch of 5 sequences and you always keep the top 5 in memory. So at the end of the decoding, you're going to have 5 different variants of the same sentence or of the same decoded output, and you can then decide which one you like best. And usually what you do is you then output the one that has the highest probability, which is not the same as the greedy, because sometimes the next token will look very good in a greedy way, but you'd better take the second most likely, because the next to next token is going to sort of make up for that and make the entire sequence even more likely. So more beam size basically means you can keep more hypotheses of the output in memory until the end. So if you just do the greedy decoding, you see you already get fairly close to these baselines. It's very, very cool, very interesting. And if you up the beam size, you surpass these baselines. Now, the way they up the beam size here, I find to be a bit, let's call it a bit cheaty, because when they say beam 5, what they mean is they keep the 5 hypotheses, and then at the end, as I understand it, if any of the 5 hypotheses passes all the unit tests, or the most, they keep it, right? So basically they give themselves the freedom to say whichever one of the 5 we output is the best, that's the one we count. And of course that's not really a match to the commercial or to the baseline system, because it can output one thing. Now, it is maybe a good practical application to give the human that, you input a function, you give the human 5 options to choose from, and it can choose and thereby decide which one the human likes best. But it is sort of, it is wonky. What I like more is this here, the beam 10 top 1. This is what you would actually do. So you could keep 10 hypotheses during decoding, and at the end output the top 1, the top likely one. And as you can see, that is better than greedy, but it is worse than where you give yourself the freedom to output multiple ones, of course. Though they say that most of the errors that this top 1 makes come from compilation errors when the target language is Java or C++. It suggests that the beam n top 1 metric could easily be improved. We leave this to future work, which this again I find valid, right? So if your method is, I'm going to keep the top 10 hypotheses until the end, and then I'm going from the top and I simply compile them and I output the first one that compiles, that's not cheating, right? That's a valid thing again. Yeah, so in that way, I can understand what they're saying right here. Okay, so they give some examples, some of which I find very interesting. So the first thing here is that, oh yeah, by the way, I've said that the tokenizer between the natural languages is shared. They make a little tweak here in that they tokenize the different languages with their language respective tokenizers, which will still end up tokenizing pretty much, this the print statement in C++ or in Java. No, actually, the print statement in Python is print, and in Java it's println and so on. But it will still, like all the if statements, it will still tokenize into the same word. But it's simply not viable to parse Python with a C++ parser. Okay, so we have looked at this. The results, this is one of the results. They look at their shared embedding space, and this is a t-SNE plot, so a 2D projection of this shared embedding space. And you can see that this is actually happening. So the different, so null, null, and none are mapped to similar locations. Println and cout are mapped to similar locations in this space. So this is exactly what we want. This is sort of a verification that this method of embedding the different languages into the same space really turns out such that whatever means the same thing is mapped to the same place. You can see here catch and accept, 2 very different tokens, are mapped to the same place simply because they're used in the same sort of constructs across the languages. Very cool. One of these examples here is quite impressive and kind of shows the difference between this and rule-based translation. In this function right here, you have a C++ function that takes a character pointer to that is called str, as an input. Now in C++, strings are, at least in old versions of C++, strings are handled as character arrays. So a string is indistinguishable from a character array. And in this case, usually what you do is you don't input the array because that would cause a copy. You input a pointer to the first, you input a pointer to the array, and that would define the string. Okay, so if you translate this, again, the type of this is simply character array. If you translate this with this transcoder system that they've built, into Java, in Java, there is a type called string, right? There's a native type called string. And is that true? I think, oh yeah, that's handled really weirdly in the JVM, I think, yes. So there is at least there is a type called string. So it would map that, it would recognize, you mean a string. Therefore, I'm going to put a string here. And it uses all the string method like string length, string character at, and so on. Where in C++, this is just an array, and you just have array accesses. Now they take this same C++ function and only change one thing. They change the name of the parameter. Everything else is the same, but now the character array is called R, okay? And they put it through the same system, and that system now outputs a function that takes in a character array called R instead of a string. And it uses, here the property length, it uses array access instead of this character at method. So simply by changing the name. And this is something where I believe the rule-based systems can be an advantage over rule-based systems, because what this here does is it simply says, oh, I've seen a lot of humans in my code base that use like stir as a variable name. And that usually means that the constructs here are like the constructs in Java where people use strings. And I've seen other places where people use, names like this right here. And usually that is used in the same context as in Java, people use character arrays, right? So in programming, it's not only important what the code actually does, but a lot of programming goes via naming of things. Like other programmers will read your code, and by reading stir right here, they will sort of assume that this is a string. Whereas if they read R right here, they will assume you're a pirate and you are referring to a character array, and they will treat the code means something different. And these systems right here, these neural machine translation systems, can actually understand that part because they do statistical inference on code that humans wrote. If you change this back to, say, input, then again, it goes back to a string and uses all the string functions. So that's fairly impressive in my mind. And definitely an advantage over rule-based systems. Of course, the disadvantage over rule-based systems is that in rule-based systems, you can almost sometimes you can even guarantee that the code does the same thing. Here, you can't. They give some examples of failed translations where, so now you run into this problem where the min function in Python is overloaded. It can either give you the minimum of a sequence, or it can give you the minimum of two things. Now this is translated to Java right here, and math.min is not overloaded in Java. It only gives you the minimum of two things and not the minimum of an array. And it still outputs that. Now, given enough data, probably it could learn because these things are all context dependent, but this is one of the failure cases of these models, of course. All right, so this was this paper. I've read that the code of this and the unit tests will be put online at some times. They are not right now. If I hear about it, I can link to it or let you know about it. Let me know what you think of this paper in the comments, share it out, and subscribe if you haven't yet. And bye-bye.